Welcome back, everyone. Today, we're diving into an interesting topic that often sparks debate among programmers.
That sounds intriguing, Bill. Why do sorted arrays tend to perform better?
Great question, Laura. One of the main reasons sorted arrays exhibit better performance is cache locality. When you access data in a sorted array, the access patterns are really predictable. This means that the CPU can prefetch the necessary data into its cache more effectively, which then speeds up processing.
I see. So, you're saying that if the data is arranged in a certain order, the CPU can work more efficiently with it?
Exactly. When data is sorted, the memory accesses happen in a more sequential manner, reducing what's known as cache misses. This helps the program run faster because the CPU spends less time waiting for data to arrive.
That makes a lot of sense. But what if we are looking for specific elements in these arrays? How does sorting help with that?
You hit on another important point.
So, if I understand correctly, binary search is much more efficient because it eliminates large portions of the list right away.
Exactly. While a linear search in an unsorted array has a time complexity of O(n), binary search in a sorted array has a time complexity of O log n. That's a massive improvement, especially for large datasets.
Wow, that's a huge difference. Now, I'm curious, how do algorithms like merge sort or quicksort benefit from operating on sorted data?
Great question, Laura. When you take algorithms like merge sort or quicksort, they leverage sorted input for better efficiency. For instance, if you're using merge sort on already sorted data, the merging process is extremely quick, leading to better performance. In some cases, it can even reach a time complexity of O(n).
That's fascinating. Does this mean that if I always sort my arrays first, I can expect them to be faster for every operation thereafter?
Not necessarily. While sorting can improve performance significantly for subsequent operations like searching or certain types of algorithms, it's important to consider the overhead of actually sorting the data in the first place. If your array isn't very large, the cost of sorting might outweigh the benefits.
That's a good point. So implementation matters a lot here as well, right?
Absolutely. The specific implementation and the algorithm used can significantly influence performance. The context in which you're processing the arrays, the size of the data, and the specific use case all play crucial roles in determining whether sorting is beneficial.
I'm beginning to see that it's not just about whether the data is sorted or not, but how we consider the entire process.
Exactly. It's all about optimizing for purpose. Depending on the operation you're performing, sorting might offer advantages, but it's essential to weigh those against the overhead.
This has been super enlightening, Bill. Thanks for breaking it down so clearly.
My pleasure, Laura. Remember, whether you're dealing with sorted or unsorted data, understanding the underlying principles is key to making efficient choices in programming.
I can't wait to explore this further. Thanks to everyone for tuning in, and we hope you found this discussion as informative as we did.
See you next time, everyone.
Thanks for listening, everyone. Please write down in the comments what topic you want us to talk about next. Also, please be sure to like and subscribe. See you next time.